Hi, welcome to Advanced Math, Unit 12, Part A, pages 3 and 4. We're doing 3 and 4 together because there's a table that kind of crosses between 3 and 4, and it's hard to go back and forth if you're not, doing. Anyway, as always, you should try to do this on your own before you look at the video. Um, Otherwise, just come in here and maybe your questions will be answered. So we're starting out with something we kind of did on the last page, which is talking about plotting a single point, and this is a more clear diagram of that, and I want to talk about ways of going about plotting points. Now, you've plotted points in 2 dimensions before. That's a thing. So if we've got a point specified here in 2 dimensions, we say it's got an x coordinate and a y coordinate. And one way you can find this point in the plane is to locate the x coordinate on the x-axis and draw a vertical line. Locate the y-coordinate on the y-axis and draw a horizontal line. And where the horizontal and the vertical lines meet, that's where you draw your point. You can do the same thing in 3 dimensions. If we have a point A with coordinates 2, 3, and 4, you can locate the 2 on the x-axis, the 3 on the y-axis, and the 4 on the z-axis. But then drawing these horizontal and vertical lines is not so straightforward. You really have to, like from the x-axis, draw a line that's parallel to the y-axis out, draw a line that's parallel to the z-axis out. And then for the y-coordinate, draw a line out that's parallel to the x-axis and one that's parallel to the z-axis. And for the z-intercept, or the z-coordinate here, you draw a line parallel to the x-axis and a line parallel to the y-axis. And where these meet, it's going to be, oops, not that, we drew red. It's going to be here, here, and here. And then if you draw a line that's from here parallel to the x-axis, from here parallel to the y-axis, and from here parallel to the z-axis, where they meet is now the point represented by 2, 3, 4. And if you do this by drawing these lines out, what you end up with is sketching a 3-dimensional box just to figure out where this point should be drawn. Now, it's true that we're working on a 2-dimensional surface. You end up plotting this point A on a 2-dimensional surface, but because we're drawing it with this x-axis at an angle kind of coming out of the page, we can think of this as a 3-dimensional drawing that we look at. Say, we can look at this box and say, oh, it looks like a 3-dimensional box. Yeah, every photograph you've ever looked at is a 2-dimensional representation of a 3-dimensional space. So we're doing the same thing here with the sketch. We have a 2-dimensional drawing that represents something that's actually in 3 dimensions. And it can, for some people, it takes some practice in recognizing that. Another way you can plot a point is, and I'll show this in the 2D version, is you can draw a path. So for example, this point on the left, a equals 3 comma 4. If I start at the origin and draw a line out along the x-axis that's 3 units long, and then draw another path that's parallel to the y-axis that's 4 units long, at the end, I'll be at point A. It's at the point 3, 4, and I did it by making a path. You can do something similar in 3 dimensions. Let me go to blue for this. If I start at the origin and draw along parallel to the x-axis 2 units, that gets me the 2 in the 2, 3, 4. Now I want to draw parallel to the y-axis for 3 units. 1, 2, 3. Now I haven't lined up sort of below this 3 mark on the y-axis. I've drawn a segment that's as long as 3 units on the y-axis, but it started over here and ends over here. So it's actually a little bit to the left of that. Now, continuing from this point, I want to draw up 4 units parallel to the z-axis. 1, 2, 3, 4. And so I've got 3 paths drawn. This path is 2 units long, this path is 3 units long, and this path is 4 units long. And I end up at point A on my drawing. So either of these methods is acceptable. If I'm asking you to plot a point in three-dimensional space, either of these is a good technique for getting that done on a piece of paper. All right, getting back to the bird ranch. Um, so the roof of the bird cage on the Yorkshire Canary enclosure is it's a plane and it's tipped at an angle. So just as we have equations for lines in two-dimensional space, there are equations for planes in three-dimensional space. And we may want to be able to represent that Yorkshire Canary cage roof as a 3D plane equation. So how do we do that? Again, I'm going to draw a comparison to the two-dimensional case. So you've seen before equations for a line in this form, this general form, ax plus by equals c. And if you wanted to plot that on a two-dimensional graph, you could rearrange it so it's in y equals mx plus b format. Or you could do what some people like to call a cover-up method by finding the x and the y-intercepts. To define the x-intercept where the line crosses the x-axis, that happens when the y is equal to 0. And you can solve for that by rewriting the equation such that the y term is taken out because y is equal to 0. So that would be the equation ax equals c. Likewise, to find the y-intercept, you set the x equal to 0. And that would take the x term out, and you'd get an equation that looks like by equals c. Three-dimensional case, it's the same idea. You've got a plane floating in the three-dimensional axis system somewhere. If you wanted to figure out where that plane crossed the x-axis, the x-intercept, you could say, well, that's going to happen when the y-coordinate is 0 and the z-coordinate is 0, and that will take out the y and the z terms, and you'd end up with an equation that looks like ax equals d. For the y-intercept, that's going to happen when the x is equal to 0 and the z is equal to 0, and that would give rise to an equation that looks like by equals d. And finally, for the z-intercept, that will happen when the x is equal to 0 and the y is equal to 0. And that would give rise to an equation that looks like cz equals d. All right, now let's go to the next page and see how this, page 2. So recapping a little bit, we were looking at ax plus by equals c. X-intercept, you set the y equals to 0, so in that case you have ax equals c, and to solve for x, you divide both sides by a, and that gives you x equals c over a. And if you're doing the y-intercept, you'd start with the equation by equals c, and so the y-intercept would happen, divide both sides by b, at the points at c over b on the y-axis. So you do similar algebra for the three-dimensional case, and you'd find the y-intercept is going to occur at d over b, and the z-intercept will happen at d over c. Now, you don't really need to remember this formula. When you find these x-intercepts, you'll typically be working with numbers, and you'll just, I hope, naturally figure it. I'll show you an example. It'll be obvious, I hope. The second thing we're going to worry about here is how do we draw these things on a plane? How do we actually represent them? I mean, how do we represent a three-dimensional plane on a two-dimensional piece of paper? And again, I'm going to draw this comparison with what we've done in two dimensions before with a concrete example. So here's an equation for a line x plus 3y equals 6. And if you use the same method we used before to find the y-intercept is going to happen when x is equal to 0. So that's the case where 3y equals 6. So y equals 2. That's this point right here. And the x-intercept will happen when the y is equal to 0. So that would be the x equals 6 equation. So That's going to be right here. And so if you know these 2 points, the x-intercept and the y-intercept, you can just draw the line between them and off you go. By the way, this is a typo here. Ax plus by equals c. Okay, so that's hopefully somewhat familiar to everybody. Now, if we do it with a plane, it's kind of freaky, the same idea. So if I want to find the x-intercept, that happens when the y and the z are 0. So just sort of this point here is going to represent the x-intercept of the plane. And when your plane is crossing the x-axis, that happens when z is equal to 0 and y is equal to 0. So our equation in this case at the x-intercept is going to be 2x equals 10 because the y and the z terms go away. So if you have an equation 2x equals 10 and solve for x, that just turns into x equals 5. And so the x-intercept of the plane is at 5, 0, 0. Now for the y-intercept, that happens when the x and the z are equal to 0. So this becomes an equation that's 5y equals 10, y equals 2. And so we can see that intercept here at 0, 2, 0. That's the point where the plane crosses the y-axis. And finally on the z-axis, that happens when x is equal to 0 and y is equal to 0. So that's the equation for z equals 10. And if you solve that for z, you get z equals 2.5. And that's why this coordinate is 0, 0, 2.5. So if we've got this three-dimensional sort of Cartesian coordinate system, x, y, and z, we now can plot the places where the plane crosses those axis systems, just like we did over here. So we've got a x-intercept here, a y-intercept here, and a z-intercept here. And these represent places where the plane crosses the axes. Now, this is just a visual trick that we're doing. If we've got these 3 points in this three-dimensional grid, and we simply connect them to each other with line segments to form a triangle like this, and then shade the inside of the triangle, we're trying to get a graphical visual representation of an infinite plane by drawing just the little section that sits in this quadrant between x, y, and z. In reality, this plane goes on forever in these 3 directions. But we can't really draw an infinite plane any more than we could draw an infinite line. We have to end it somewhere. So the convention is that we draw this little triangular section that represents the plane. All right, so that's drawing planes in 3 dimensions. In the next section, I think we're going to do some examples. So get ready for that.